Welcome back to another video. So in this video I will talk about a project that I found on Twitter. It was a project where you could solder directly on a PCB like this one. And you may have seen other videos from other YouTubers have made videos about this. So let's get going. So there's a project on GitHub by their spots, solder reflow plate. And there are 3 folks that have forked and changed the solder reflow plate design original shown by other channels like Great Scott. So here it is, and it's the version 1.1, and they have made a few changes to it. So this PCB boards in this video are kindly sponsored by PCBWay. So thank you very much PCBWay for sending me these boards. I was told by people that the boards only holds a couple of reflows, and also my contact at PCBWay said that their FR4 temperature grade is upgraded, so that's very interesting. So there's a new YouTube channel called Yark, yet another radio channel. It's a small channel and it's growing, and he has a lot of interesting videos up and coming. I really wish him well, so please check him out. You know, I love power supply stuff. Anyway, I've already been testing these boards, and I've done about 5 to 6 reflows with no signs of degradation. Not sure why others have had problems. It could be that my boards do not get as hot and as fast as previous designs due to wider tracks. So we get back to that. So this one has in 1.1 has 1.3 millimeter tracks, and in the heater panel. So, and the other one had 1.15, so that's a difference there. So that can be one thing, or that what my PCBWay contact told me, that it was upgraded FR4 could be a reason, or as we will see in this video, this board that I will solder up it heats up very slowly because of this increased width here. So we don't get enough power into the board. So maybe that's why after like 6 times I think it looks pretty good. So I can actually just clean this off, as you can see here. So just flux. So that's pretty cool. Feels okay. I'm very impressed by these boards, and I have a few things to say about the PCB design though. So let's have a look. In the second screen recording here, we can see that there's a fork of After Earth Ltd, and the board feature on many other channels, including Great Scott. So I won't go into so many details about that. I just want to show you my experience of this. Yeah, so what have they done? Well, they have added a barrel jack, so we're gonna get more current into this, and they have added a resettable fuse, a in-reach current limiter, I think is this one, I think, and then there's a resettable fuse there, and then we have input capacitance, which I think doesn't really matter that much actually. Because I think the original designer wanted it to smooth out the current. However, there's nothing here to smooth it out. There's no inductor, so therefore they only get hot if they are driven at very high frequency. They get hot. So I don't think that works so very well. So, and there's also this is an improvement actually. There's a 5-act diode in there. Yeah, so it's basically in there. Pretty cool. Okay, so I started soldering the ATmega here, and the ATmega 4809 is replacing the very common ATmega 328P. At the time of the design, the 328 was not available. You know, the pandemic and everything, chip shortage. In my thoughts here, that the number of components should come down. So it's a bit crowded. And the LED should be a 2 standard single LED, not a special LED. However, it was not difficult to find on LCSC. So the board doesn't have any means of measuring current either. So we just have a it can measure input voltage. Actually, it has a voltage divider. There's two temperature measurement. This one is this is digital. This is analog. LT85. This is a Dallas 1820, I think. Anyway, this one is used with a temperature gradient, which is the highest temperature is in here, and then there's a gradient down here. You use a special formula to predict the temperature here, so you don't really know the exact temperature. So to get precision with this board is really hard. So I don't think we'll aim for that. I just want solder to melt, and in such a fashion that the board doesn't break when you do it. So that's my expectations about this. The project has LCSC part numbers baked into the footprints, meaning that they also show up in the interactive boom. This is really lovely. So it makes it really easy for me to order parts as well. But that was interesting, so I will do that in my projects also. Put the part numbers into the symbols and footprints, or the symbols themselves, because then I can get them out on the iBOM or the interactive boom. The tracks have gone from 1.15 to 1.3 millimeters. So yeah, so that means there's more current going through here at a lower resistance. So the power supply can't cope with it. And if you can, like my lab power supply, it would just lower the voltage, and then I can't get the wattage I need. So I need the resistance here to be higher, to be honest. Alright, this is just a side note. You can see my hands are really shaking here. That's because I take something called Bricanyl. It's an asthma medicine that I have. And Bricanyl is like Ventolin, which is probably better known. Yeah, and there's a lot of other ones that are steroids, things that keep your heart racing and shaking your hands and everything. So I'm not doing that. I don't use it very much anyway. So alright, so that's what it is. This is the finished board, and I'm really happy with that. I haven't cleaned the flux of it yet. I don't need to. These ones were really bad actually. They come off really easily. I don't know why that is. They're really bad connectors, but they do kind of work. So this is what the board looks like after like 5 or 6 times of use. And still fine if you ask me. So at this point I brought out my Wellman lab power supply, 30 volts, 5 amp capable. Perfect. I was thinking that I didn't have a power supply that can supply this, but thankfully now I can also limit the current, which was proving to be important. However, elsewise the resettable fuse would have helped, but it will just ruin the project. So you may notice that I'm using the Pi 50412 PCB as a display here. The display is too large, but it just stretched out the image to fit. So that's cool. That's something happening in the driver, I think. So I ordered some correct smaller displays. We will see those later in the video. Since I first tried it without a display, I missed the option to set the board resistance. It is possible to set it by holding the buttons at power on. So the first time you power it on, it should show that you need to set the resistance. The flyback that I was talking about earlier, which is down here, the board resistance is measured over the flyback diode, sitting at the input of the heater bed. In these initial tests, we see that we get overcurrent. That is something software is supposed to prevent. You see, when the board is cold, the resistance is at its lowest, and more current will flow. In fact, 12 volt into 1.25 ohms load is way over 5 amps. Therefore, you put your board's resistance measured at the room temperature. This doesn't seem to do anything for me, maybe because the board is missing the ability to measure current, I'm not sure. Though it does have input voltage and to measure, and it knows the resistance, so shouldn't that be enough? and it kind of knows the temperature as well, so it can calculate the resistance at that temperature. It's a new day, and here we have the new display. Really happy with that. I bought it from a Norwegian seller, so I don't have to get that import taxes. So here we have our initial test number 1. We notice 2 things here. The current is ramped up, that means a pulse width modulation from the microcontroller. Once it gets to 5 amps, the loud power supply switches to constant current mode, limiting the current by dropping the voltage. This means less power is going into the board now, and the solar process takes longer. This is not good. We also notice that, as expected, the board resistance goes up with heat. As indicated by the loud power supply, now increases the voltage to maintain 5 amperes. Here we can see an overshoot. Therefore, we can see the board is now taking less power. All in all, we see that the pitch regulator is not well tuned to my board, and the heating is low. It is not getting the power it needs. Why is this? Why was the trucks increased? I don't know. The board resistance at high temperature is now just too low to accept 12 volts 5 amperes. In this test I tried one of older prototypes, a tiny PCB adapter. So it does get this thing hot enough to melt, but that's that, I think. Nothing special. So let's try some solder paste. Now, this is clearly not working. So let's now you will be set over to the other guy, which talk directly to the camera. I'm gonna try and heat it up on the oven over here. See if it gets better. It seems very dry, or it's cold. Yes, this is 0402. Yeah, this is too small. Oh no, it's sticking. See, okay, it wasn't so hard to place it, but wow, look at that. This is not the correct part. Okay, and I also have a 08, I think, or is it 0806. But that one is also incorrect. But that's what I got on hand right now, I'm sure. Okay, I know where I can find 04. Well, it seems to fit anyway, so. Okay, there you go, so let's go. There you go. Turn on this one. There, so let's try this. It's not very good, but okay. 140. With a little bit of soaking period there, you can select a straight slope. There we go. Now we'll hear 1 kilohertz tone. That's because I turned down the switching frequency of that MOSFET under there. Because 64 kilohertz seems to heat up those caps a lot, so I don't think that didn't work so well. So this seems to be working. You can see the voltage is dropping. That's my power supply, which is limiting the current to 5 amps. So if it drops too much, it will reset the microcontroller and the heating will stop. So yeah. And while the board is heating up, you can see here the voltages are rising. So and the funny thing about that is that when the board gets hot, the resistance of the copper is increasing. So therefore we can put more power into it. So that's cool. So it's the same amps. Yeah, it's a bit hard to explain. Maybe I don't understand it myself even. But here goes. Look, there seems to have been while I've been talking, it seems to be soaking. This is probably soaking. I never really thought about that before. So what soaking really means. But it looks soaked, and you can even see all the individual solder balls there. So I think if it gets to, like now it's at 82C, if it gets to 100 it will start to melt. And this is called the soaking period, because now you see it's the set point, which is now 91C, is higher, or it's holding, so the regulator can wait for the power. Now something interesting is happening, I think, because we are getting more voltage, more temperature than the set point, which is a kind of strange. I think that's an overshoot, but the regulator should drop. Yeah, now it's dropping. You see this value is right, so we got a timeout. I did have my fan on in here, so it could have been too much draft for it. I think we will repeat this experiment, and flashing or something. I don't think. Anyway, oops, something is starting to happen here. Whoa. Oh, let's try help it a little bit. You're not supposed to go that way, that's for sure. Oh, there you go. Well, that actually did work. It will continue to heat a little bit, so I don't think that's a good thing. I don't know, because the board is really, really hot now, so it should actually start to cool, I think. But let's just wait for it. So maybe I will do a setting here in the firmware. Not 140, but let's say 130, because this one is seeming to go too far. And we don't want to blow up anything. So. Yeah, this is frying the board, so I don't think this is good. Or what do you think? Let me know. Well, it's at 140 now, the regulator set point. So let's see what it does. And since we are so close, we should see the... oh, there it stopped. Well, it timed out. Well, it doesn't say timeout. It actually just says cooldown. So this time it actually worked. But as you can see in this scope image, it's really, really hot still. So I think that was a bit long. Maybe I should... we could try to change or calibrate the temperature sensor over here. But I think I don't want to touch any of those parts of the code. So yeah, so maybe have another setting, not 140 but 130 as well. Actually the original board could go down to much lower than 100, so I don't know what they did with this firmware. So yeah, now it seems to solidify at last. So yeah, now it should be stuck. Yeah, that's soldered. Right, so I'm just playing around with the footage that I have, and this is the soaking period that I was talking about that failed, and it's maybe easier to understand what's going on if I speed it up. Like here, you can see it starts to reflow actually. But then the regulator says timeout. That's where it stops. So it was about to solidify, but the microcontroller said no, enough is enough. So that's what happens. Yeah. Just a quick edit. I added 120, 130 to that max temp array to this code, which is in platform IO, which is VS Code by the way. It's really cool. Connected here to the Arduino, acting as an UPD-TI, connected further into this board, and then we just hit upload. Compiles and uploads. It's a bit slow, but yeah, that's what you get, I think, if you use Arduino with UPT, I think. Weird name. So yeah, so there it goes. Programs. And there it's in. So we can try. Yeah, now we have 120. Before it only got down to 140. So that's great. So now we can play around with that. But now I need some sleep. So it's a new day and I'm going to start filming again. I'm going to do another run of this. So, and this time I'm going to use a 0604 component. It's a 0603. Right, so with this is yesterday, and today I'm going to use 0603 components, which I have up here in this little booklet thing here. So hope it doesn't fall apart, the whole shelf. It's a sample book with a lot of components, so I'm just gonna pick a random one. And yeah, I think it has it only has 0603, but it also has capacitors. Right, so let's try get one out. 30K, I probably won't use 30K for anything, so get out a couple of these. Just gonna drop it onto the oops. Yeah, that one's gone, I think. Hold on. There it is. Just gonna drop it onto that board over there. So, and there I lost the second one. Well, no, it's there. There we go. There we have 20603 ready to go. Alright, so this is the SMD291AX chip quick, and it has a shelf stable, well, it's shelf stable. It's not one of those you have to keep in your fridge at all times. So it works for me. And this radiator is a water radiator, and I can touch it without pain, but it's painful to hold. I think it's about 45 degrees C or something, 40 C maybe. So just leave it on there for 3 minutes. It should be fine. That works for me. I guess I lost the point of this clip. The point is that the flux sticks better to the board. The flux sort of rejuvenates when you heat it up a little bit. So put it on your lamp or anything just for a short amount of time, and it will be better. Right, so this time I gotta clean the tip a little bit because the components were sticking so much to the tweezers last time. So yeah, there you go. And this time I'm not going to use so much that I used yesterday, because that was a atrocity, right? There you go. I think this is good. This is better. It's not as excessive as yesterday. This one in. There you go. All right, so let's go. See if we can zoom in on that thing. So I've just turned on the power. We have the new program in here. It says 120 now. That's maybe a bit low, so I think 130 is better. So, and we don't want soak because that took so long. So while this is going, hopefully it's not failing while I'm talking. So I'm just gonna see that it goes up to 5 amps. And yeah, there it went. Yes, now the power supply is actually going over 5 amps, so it's regulated. No, it's yeah, I can show you. It's at constant current, so it's dropping the voltage instead. This is supposed to be done by the microcontroller, so we don't overload the power supply. But I guess we'll have to come back to that another time maybe. And because when the board is heating up, the resistive goes from 1.2 ohms to about 2 ohms or something, so therefore the regulator has to compensate for that. But anyway, we can already see that there's some soaking going on. Maybe it's a bit early. This time I'm not speaking directly, I'm not talking into anything, so I don't push air onto the board. Yeah, so what I wanted to say about those numbers, like you can see up here, you can see the numbers. They are not correct or anything, so you could go all the way to the moon to calibrate this thing. It will never be correct because this one is reading the temperature outside the board, so it will always be incorrect. However, the original designer has made a calculation that there's a temperature gradient, so that's what it's using, and I don't really care about that. I just want solder to melt, and I don't want to fry the board, and I'm happy with that. So if I can set it to 130 or 120 on this display, and I know that will work, that will work for me. So, and that's the same. Lots of people come and they ask, can I what soldering, what temperature do you set your solder iron to, right? The solder iron. And well, that depends on your solder iron, right? But I set it to like 280. If I just solder a thin cable, maybe 260, 270, maybe even lower. Once I go down onto a circuit board, I will try maybe up to 300, maybe 290, because it gets so slow. It depends on your chip as well. If it doesn't have like a real mass, Like this one has a really good, this is one of those Hakko clones. It has a really massive tip at the inside here, but it goes gradually smaller at the tip, so it kind of has a lot of oomph to it. No, there it stopped again. So I think we have to go 140. So what do you think? Should we try this experiment again? Just let it cool down? Not sure. I think I will do that actually, because I don't think it's correct that we should start at such high temperature. But I'm very impatient now, so I will try anyway. Slowly coming down. So yeah, you should probably need to edit some parameters there. Oh, now it's reflowing. Nice. And it's reflowing at 135. Maybe 135 or 136 or something is what I should aim for. So, but anyway, it hasn't come to 140 yet, so just soldering because of this overshoot, I think. But it's good. It hasn't reflowed everything yet, so it should go on for a little bit. So it's 133. I should probably try this again, but from a cold start. .6 amps. And the regulator is going up now. It's because the set point is going up. 3 amps. Now it should solder again. I really hope it does. Or else it's a failed experiment. Oh, the program stopped again, right in the middle of the solder phase. So I think maybe I need to set it to 140 and start from the beginning. So right, so we have another setup here, and we're going to try it again, this time at 140C. That this one will go first. But I'm not sure. So now we are watching this one. So, oh, there it goes. Actually, I seem to be in the wrong. It's the other one that goes first. Yeah, there it goes. Nice. And there it turned off. Yeah, so for this board maybe we should do... And now all the solder transferred over here, so that's a fail. And here. It looks fine. Yeah, we will get the hang of it sometime. I guess with a stencil it will be more controlled how much flux I put on it and everything. So, but yeah, that seems to work fine. I'm happy with this, and it's cooling down and everything. So 140 seems to be working rather well for this. Well, it's not perfect, but it does work. So, and I can easily fix that one. I wish it would just work the first time, but nope, it didn't. But yeah, so I think that will be enough for this video. I think I will just turn this one off now, and let's see. Let's end the video here. I hope you liked the video, and I thank you again, PCB for sending me these boards. And also another thing they said was well, I'll probably see that in the beginning of the video anyway. So thank you very much for watching. Hope it wasn't too confusing. What do I want to do with this PCB? Well, I don't think I will continue developing it. Maybe if I get on a whim or something. I didn't really like the improvements, or in Tuddle's improvements, because this thing here, which doesn't really help, it doesn't. I think the idea here was to use PWM to smooth out the current at 64 kilohertz, and but it doesn't do very much. And if that would work, then it would have an inductor like in a switch mode power supply. So, but PWM does work. However, I don't think it was a good idea to increase the width of these tracks. So it got too low resistance for it to be enough to put power into it. What I would like to do maybe is to increase, maybe I'll continue the video. I'll make a second part, because I have this one. It's just an Allegro ACS 712, and this one is something of a wonder. It's let's see. There you go. We can put it in here. So ACS 712, it's a wonder. How does it work? Well, it's got isolation. It has an operational amplifier. So what it does, you put current through it on this side. That's why you have the big terminals there. And whatever you put on this side doesn't have to be low side or high side. It's completely isolated. As you can see here, it's isolation in between these two upper and lower layers. And the current goes through here, through a little notch, and then it produces a magnetic field. And that magnetic field is read and put into amplification. And so this part is not digital, it's completely analog. So when it's 2.5 volts, the current is 0. If it's negative, or if it's lower, it's a negative current. If it's higher, it's a positive current. So this one is really great, and because of this isolation, it won't affect the microcontroller in a bad way. So the plan I have then is to be able to measure the current going into this device. So I can adjust the regulation, because it doesn't have any means to adjust the current. And then if I have a little bit of higher resistance here, it can kind of compensate from production from board to board, because let's say you have like a solder iron. Well, it says maybe 60 watts, but it doesn't really put in 60 watts all the time. Or if you have like one of those hot air rework stations, if you put full effect, if you remove the controller, put full effect, it will turn white, red hot glow. So it has the potential to heat really fast. So
therefore there's a margin, so you can regulate that. But here there's no margin. It's just you can't put enough heat into it. Also, maybe if 24 volts would be better, so you don't have to put so much current into this thing. So, but then you will have to have components that can handle 24 volts. So, I'm not sure what's best here. So, but anyway, that's what if I make a second video, I will probably try to add this one. Maybe I'll just remove the fuse here and then connect this in between so I can measure the current. And I have the regulator regulate before it gets to 5 amps. Because we saw my bench power supply, it kept on regulating that current or limiting that current, which doesn't happen if you have a power brick. That will just maybe shut off and everything is not working very properly. So we need to get power to where it's supposed to be. So that means maybe high voltage, high resistance here. And higher voltage is a good thing, because then you don't have to put so much current. And if you don't put so much current, these components on the input here, like this switching transistor, this input transistor, and this fuse, it doesn't have to dissipate so much power. Its power is dissipated here. So that's what I'm thinking. Okay, thank you very much for watching. That's just my thoughts for this project, and have a nice day.